Hi everyone, welcome to my Max Academy. In this session, we'll continue with the chapter Relations and Functions, which is chapter 1 from your 12th standard CBSE Mathematics. So we will continue with the next set of or types of relations. So I am at page number 2, definition 3, page number 2 in your textbook, definition 3. So we have some more types of relations. That is, what we have, the next type of relation is reflexive relation. Reflexive relation. Now, a relation R on set A, a relation R on set A is said to be reflexive relation. Said to be a reflexive relation if A comma A belongs to R for every A belonging to set A, for every element A belonging to set A, then we call such type of relation as reflexive relation. What is the reflexive relation? A relation R on set A is said to be a reflexive relation if this condition is satisfied. A comma A belongs to R for every element small a in the set capital A. Right? So the definition may be a little bit confusing. I'll give some examples, then you can understand this in a better way. For example, if I take a set A, suppose we take set A is 1, 2, 3, and we define a relation R on set A, which means R is a relation from A to A. Right? Suppose if R, I am writing the relation set R, which is set of all ordered pairs. I am writing it in the roster form, which means I am listing some of the elements. Suppose if the relation is like this: 1, 1, 1, 2, 2, 2. Right? So some elements I am taking from the Cartesian product of A cross A. Right? Relation R is what? A subset of A cross A. So I am taking few elements from A cross A. I am listing this. So suppose 2, 2, then 2, 3, and then suppose 3, 3. Now, so which means these elements are present in A cross A, because A cross A is what? A cross A is 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. So from the total of 9 elements in A cross A, I have taken some elements. Now the question is this relation reflexive? Now we need to check whether this relation is a reflexive relation. Now to check that, so what do we do is we have to check this condition: A comma A. Both should be same. The first element and second element should be same. That ordered pair should be in R, and that should be true for every element in A. Now we will have to take one element from A. Take the first element 1, which is your small a. I am taking 1. Then 1, 1 should be in R. You have to check: is 1, 1 is in R? Yes, it is there. 1, 1 is present in R. Now again, next one is, take the second element 2 from set A, 2. Then 2, 2. Is it present in R? Yes. So take the third element 3. Then you have to check whether 3, 3 is in R. 3, 3 is in R? Yes. So all the 3 elements, for each element in A, for every element, so it should be true for every element in A, that element should be related to itself. If I take the element 1 from A, then 1, 1 should be in R. If I take the element 2, then 2, 2 should be there in R. If I take the element 3, then 3, 3 should be there in R. Then we call this as a reflexive relation. See, it can have other elements. It can have 1, 2, 2, it can have other elements, but it must have, for every element of A, that element should be related to itself. Which means if I take the element 1, then 1, 1 should be here. Second element 2, 2, 2 also should be there. Third element 3, 3 also should be there. So every element is there. Even if one element is not there, one pair is not there, then it is not reflexive. So in this case, it is reflexive. So this relation is a reflexive relation. Reflexive relation, because it satisfies this condition for every A. For every element A comma A is in R. Right? Now we'll take one more example. Suppose for the same set, I'm taking another relation. Suppose this is another relation. Suppose this is R1 relation. Yes, I'm taking another relation R2. Taking another relation R2 from ZA to ZA. Suppose if I write this as say 1 comma 1, then 1 comma 2, 2 comma 1, then 3 comma 3. Now the question is it a reflexive relation? So for that again we need to check whether for every A in A, the element is related to itself, which means I will take the first element 1 from A. Then I have to check 1 comma 1. I should put 1 here for both. 1 comma 1 belongs to R. I have to check this. Yes, it is there. Okay. Second element 2. Take the second element from A, which is 2. Again 2 comma 2 is in R. 2 comma 2 is not there in R. The moment you see even one element is not related to itself. Right here 2. I have taken an element 2 from A, but 2 comma 2 is not in R. Therefore, we have to stop and say R is not reflexive. We will say 2 comma 2 belongs to A. 2 is in set A, but 2 comma 2 does not belong to R, which means 2 comma 2 ordered pair is not in this set R2. I'm just calling this relation as R2 relations. Another relation. I'm just naming this is R1 relation, which is R2 is another relation, which is this, and 2 is in A, but 2 comma 2 is not in R2. Therefore R2 is not reflexive relation. Reflexive relation is not a reflexive relation. Clear? So which means for every element in A, the ordered pair of 1 with 1, 2 with 2, 3 with 3 should be in that set, that relation set. Then you call such relation as reflexive relation. Even for one of the elements in A, if that, suppose here 2, but 2 comma 2 is not there, but 2 is in A, but 2 comma 2 is not there. Even if it fails for one element which is in A, but that element comma the same element, just 2 comma 2 is not in R, then you will say that R is not reflexive. 1 comma 1 may be there, 3 comma 3 may be there. For 3, 3 comma 3 is there, for 1, 1 comma 1 is there. But for 2 also it should be there. For every element in A, that's the meaning of this. For every this condition should be true. Even, which means even for 1, if it fails, R is not reflexive. Clear? So this is how we define. These are the two examples for. One is for reflexive relation, the other one is for not reflexive relation. Fine. Now we'll go to the next type. So you can take the notes. You can pause the video and take the notes. The next one is, I'm erasing this. Next one is called as reflexive view of sound. The next one is symmetric relation. Symmetric relation. The definition is a relation R on set A is said to be symmetric relation. Symmetric relation if A comma B belongs to the set R, then B comma A should be in R. Or they may say if A comma B belongs to R implies, they may put the symbol which means implies, or you can say then B comma A should be in R. And this is true for all A comma B, the elements A and B in set A. For all A comma B, A and B, element A and B in set A. It's not the ordered pair A comma B. It is element A and element B. It's true for all element A and element B in A. So which means whenever if you see a pair A comma B in R, then the reverse should be in this. The reverse should be in this. So for example, we'll take one more. So I will give you examples so that you can understand the definition. So I am repeating the definition. A relation R on set A is said to be symmetric relation. If A comma B is in R, then the reverse B comma A also should be in R. Then you call such a relation as symmetric relation. So we'll take an example. So let's take the same example, same set A. So for example, suppose I have a set A which is 1, 2, 3, and R is a relation from, suppose R1. I'm defining one relation R1 from A to A. Just name of the relation, call it as R1 relation. Right? Suppose if R1 is like this, say 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 3, 3 comma 2. Fine. Now the question is this relation? It's a relation because it's a subset of A cross A. Anything which is subset of A cross A is called as a relation. So it's a relation. I'm writing the relation in the roster form. Now this relation, the question is this relation R1 is symmetric? Now we have to check whether R1 is symmetric. To check whether this relation R1 is symmetric, right? What we have to do? We have to check one element. This is A comma B. It is in R. Then the reverse of this should be in R. So what is 1 comma 1? The reverse of 1 comma 1 is also 1 comma 1. So this is your A, this is your B. Now AB is in R, which means this 1 comma 1 is in this R1. The reverse, what is the reverse of this? Reverse is again 1 comma 1. That should be in R. It is there. Now let's take this element. This is A comma B. This is A, this is B. Right? A comma B, which is 1 comma 2, it is in R. If this is in R, the reverse of this. What is the reverse of this? 2 comma 1. It is there. It should also be there. The reverse of this, which means B comma A. What is B comma A? B comma A means 2 comma 1 should be in R. Whenever A comma B is in R, then the reverse also should be in R. Then you call such relation as symmetric relation. Again, we have to check this for every element in R. Here we say for all A comma B in A and B in A means, which means for any element in R1, whenever this is satisfied, the reverse also should be there. Right? Again, let's take this element 2 comma 1. You take this as A comma B. What is the reverse of 2 comma 1? 1 comma 2. That is there in R1. So it is satisfying for this condition. So this is also it is satisfying. It is also dissatisfying. It is also dissatisfying. The reverse. The reverse of 2 comma 1 is 1 comma 2, which is there. Now take 2 comma 3. 2 comma 3 is in R. What is the reverse? Whenever you take an element, you should check whether the reverse is there in the R. Now 2 comma 3. What is the reverse of 2 comma 3? 3 comma 2, which is there. So this is also satisfying this condition. Then again take the next element 3 comma 2. What is the reverse of 3 comma 2? It's 2 comma 3, which is here. So this is also satisfying. So for every element, it is satisfied. So whenever A comma B belongs to R, then B comma A should be in R, which is true. Which means whenever you take anything, any element, the reverse of that should be in the same set. Any element should be true for every element in the set. So then we call so here R is symmetric. Symmetric relation. R1. I mean this relation R1 is called as a symmetric relation. Now let's define another relation R2 on the same set. Suppose R2 is another relation, which means I'm going to write some numbers with some subset of A cross. Okay, suppose say let's take 1 comma 1, say 2 comma 2, then 1 comma 2, 3 comma 1, 2 comma 1. Now the question is this relation R2 symmetric? So to check whether it is symmetric or not, what we should take? We should take one element and then do the reverse and check whether the reverse of that is there. This is A comma B. Reverse is B comma A. The 1 comma 1. Reverse is 1 comma 1, which is there. So it is satisfied for this element. Now we should take the next element 2 comma 2. Reverse of 2 comma 2 is also 2 comma 2, which is there in the set. So this is also satisfied. Then 1 comma 2. What is the reverse of 1 comma 2? This is A comma B. Whenever A comma B, whenever you find an element A comma B in this set R2, then the reverse of 1 comma 2 should also be in R2. What is the reverse of 1 comma 2? 2 comma 1. It is there in R2. This element is present. So for this also we checked. Tick mark. Again for 3 comma 1. Now what is the reverse of 3 comma 1? 1 comma 3. 3 comma 1 is there, which means this is there. If this condition is there, then this also should be there. Now this is 3 comma 1 is there. Now then the reverse should be there. Is the reverse of 3 comma 1 is what? 1 comma 3. Is 1 comma 3 present here? 1 comma 3 is not there. If 3 comma 1 is in this set, then 1 comma 3 also should be in this set. So 3 comma 1 is there. What is the reverse of 3 comma 1? 1 comma 3. That should be there. The reverse. A comma B is in R. So this element is, think this as A comma B. A is 3, B is 2. Then this is also in R, which means B comma A is also in R. B comma A is 1 comma 3. Is 1 comma 3 is there? No, 1 comma 3 is not there. So it is failing for this element. Even if it fails for one of the elements in the relation, it is not symmetric. So it is not symmetric. This is not symmetric. Symmetric relation. Clear? Fine. Now, so we have seen one example where it is symmetric and another example where it is not symmetric. So for each element you have to check whether the reverse is there. If A comma B is there, then B comma A should be there, and it should be true for every element in this relation. Even if one element, if it fails, then you will say it is not symmetric. Here it is true for every element. 1 comma 1 reverse is 1 comma 1. 1 comma 2 reverse is 2 comma 1, which is there. Then 2 comma 1 reverse is 1 comma 2, which is there. 2 comma 3 for this reverse is 3 comma 2, which is there. For 3 comma 2 the reverse is 2 comma 3. So for every element this condition is satisfied, so that it is called as symmetric. Here it fails for this element, therefore it is not a symmetric relation. Fine. So next what we have is transitive relation. Transitive relation. Transitive relation. Next one. Next type of relation is transitive relation. Now, so a relation R on set A is said to be transitive relation if A comma B belongs to R and B comma C belongs to R. Whenever you see such two elements where A comma B is in R, another element B comma C is in R, then A comma C should be in R. A comma C should be in R. Then we call this as transitive. Whenever you find two elements like this, A comma B, then the second element should start from the ending of this. A comma B, this should start from B comma C, the continuous. A is related to B and B is related to C, then A should be related to C. A should be related to C. A should be related to C. If that is also there, the third element, which is A comma C, then you call such a relation as transitive relation. It should be true for any two elements that you find like this in your set R. Any two elements like this, then the third element, which is A comma C, should also be in R. Then we call such type of relation as transitive relation. Now let's take an example for that. Suppose if we take an example. Let's take an example. Suppose again A is the set 1, 2, 3. Then I'm defining a relation. Suppose R1 is a relation from A to A. Then R1 I'm writing it as some subset of A. A cross A. Some subset of A cross A. I'm going to write. Now what is that? Suppose if I write this as suppose 1 comma 1, then 1 comma 2, 2 comma 3, 1 comma 3. Now this is my relation. Now the question is this relation transitive? Is this relation transitive? Then what we should see, we should take all the two elements which are in this form. Right, let's take this element 1 comma 1. This is like A comma B. Now let's take the another element which is starting with B, the ending of this. So this is your A, this is your B. Now let's try to find another element which is starting with B, which is starting with B, right? Which is this. Now take these two. Now 1 comma A comma B belongs is in R1. B comma C, this is your B and this is your C, which means A comma B, it is ending with 1. So this, the next element should have 1 as the first element. Then this can be anything 2. Now this is like A comma B and B comma C. Both are in R. Now which means A comma C. What is A comma C? A comma C means 1 comma 2 should also be in R1. Yes, 1 comma 2 is there. If you take these two elements like A comma B and then B comma C, then A comma C, that also should be there. Our A comma C is what? 1 comma 2 and 1 comma 2 is there. And again we should check for every pair in this, and that pair should be like this, A comma B, and then the next two elements should start from the ending of B. Now let's take, so this is for these two to satisfy. Now let's take this element and this element. Now 1 comma 2, now this will become like A comma B. This is A, next element. I'm erasing this. Now A comma B, this is B comma C. It's ending with 2, then it should start with 2. So 2 comma 3, then 1 comma 3 should be there. A comma B, which is 1 comma 2, is in R1. Then 2 comma 3 is also in R1, which is B comma C. Then A comma C, what is A comma C? 1 comma 3. 1 comma 3 also should be in R1. Is 1 comma 3 present? Yes, it is there. Clear? So again, we'll have to take, now these two we cannot take. These two elements we can't take because this is like, if I take this as A comma B, right? We're erasing all this. Suppose if I take this as A comma B, then I cannot take this because it should start from 3. So I can't take these two elements and check. Right? So don't say that 2 comma 3 is there, so 3 comma something should be there. So this condition is failing. No, this condition can fail. Whenever these two elements, whenever you are able to find such two elements, then this element should be in R. If you are not able to find these two elements, that is okay. It doesn't make this condition fail. It doesn't make, if you are not able to find such two elements, then also it is transitive. If you are not at all able to find any two elements, here we could find two elements like this. If you are able to find two elements like that, then for every element, the two elements, this is one element, this is another element. For every element, it should be true. Every pair of element which is in this form, then A comma C should be in this set. Right? So here 1 comma 2 is there. This is A, this is B. Then BC. It is ending with 2, so here it's starting with 2. So 1 comma 2, 2 comma 3. Therefore 1 comma 3 should be there. Yes, it is there. We can't take these two elements because they don't satisfy. So we need not check this. You say any other pair is there. We can take one ending with 1. We can take these two. 1 comma 1 and 1 comma 3. Right? Let's take this. This is A comma B. This is B comma C. This is A, B. Now this is B, C. Now 1 is related to A comma B, then B. It's ending with 1, so starting with 1. Right? So 1 comma 1, again 1 comma 3. Which means 1 comma A comma C. A comma C is what? A is 1, C is 3. Then 1 comma 3 should be there, which is there. 1 comma 3 is here. So it is satisfied for every two elements which are in this form. Whatever two elements which are in this form, A comma B and B comma C, then the third element A comma C is also in R1. Therefore it is transitive. It is transitive relation. It is transitive relation. So it should be true for every two elements which are in this form, A comma B. Whenever you find two elements like this, A comma B and B comma C, then third element which is A comma C should be in R. Should be true for any two elements which are in this form. Every two elements or every pair which is in this form, then the third element A comma C should be in that set, the relation set. Then you call such relation as transitive relation. Now let's take another example. Suppose taking another relation R2 on the same set A. Okay. Suppose I say 1 comma 1, 2 comma 1, Fine. Then say 1 comma 2, then say 2 comma 3 and 1 comma 3. Fine. Now let's take one by one. Let's take two pairs. So now this is 1 comma 1. Now we need to check the element which is starting with 1. This is 1 comma 2. So let's take these two elements, 1 comma 1 and 1 comma 2, which means A comma B, B comma C, then A comma C should be there, which means 1 comma 2 should be there, which is there. Right? Then take the next. Then again take the element which are ending with 1. This is ending with 1. This is ending with 1. So take the other element which is starting with 1. This one. So now again 1 comma 1 is there, 1 comma 3 is there. So A comma B, B comma C. Therefore A comma C. A comma C means 1 comma 3 should be there, which is there. Which is there. Therefore it is satisfied for this. So again we'll have to check for every pair like that. Now let's take this element. Now 2 comma 1. Now find all the elements which are starting with 1 here. It is starting with 1 here. Even this is starting with 1. So suppose if you take this element and this element, 2 comma 1, this is 1 comma 3. So wherever this is ending, you have to take the next element which is starting with 1. I could have taken this also. I'll come to this. If you take this and this, 2 comma 1 is there and 1 comma 3 is there. Therefore 2 comma 3 should be there. This is A comma B. A is 2, B is 1. Here B is 1, C is 3. So A comma B and B comma C both are in this set R2. Then A comma C should be there. What is A comma C? 2 comma 3. Is 2 comma 3 there? Yes, it is there. For these two elements, this element should be there, which is there in this R2. 2 comma 3 is there. But let's take these two. So you have to take all two pairs which are in this form. You have to check for every pair which are in this form. Even if one of the pairs fail, then we will say it is not transitive. Now let's take these two. 2 comma 1 is there. Then 1 comma 2 is there. It is in the form of A comma B. This is A, this is B, this is B, this is C. A comma B, B comma C. A comma B, B comma C. Then A comma C should be there. What is A comma C? 2 comma 2. Is 2 comma 2 present here? No, it's not there. 2 comma 2 is not there. So for this pair of element, it is like this. I am able to find two elements like this, but whereas this A comma C is not there. So 2 comma 1, which is A comma B, then 1 comma 2, which is B comma C. So A comma B belongs to R, B comma C belongs to R2, but A comma C, which is what is A comma C? 2 comma 2, but it is not there. 2 comma 2 is not there in this. Therefore, it is not transitive. Here it is passing. If I take this and this and this, for these two elements, this is the third element. Right? For this and this, the third element is this. For this and this, the third element A comma C is this. But if I take these two elements, A comma B and B comma C, 2 comma 1 and 1 comma 2, then A comma C, which is 2 comma 2, should be in this set. But 2 comma 2 is not there in this set, in this R2. Therefore, this is not transitive. It is not transitive relation. It is not a transitive relation. Clear? How we find what is reflexive, symmetric and transitive? Fine. So we'll do some more example. I'll explain in detail. We'll continue on some more examples. Pause the video and take the notes. I'm erasing now. We'll go to some more examples on these reflexive, symmetric and transitive relations. Fine. Now we will take some examples. So I will write the definition of reflexive again here. So reflexive relation means A comma A should belong to R for every. So this symbol is say for every. This is simple to say for every or for each. For every A belonging to A, that is this reflexive. Then symmetric relation is if A comma B, if A comma B if A comma B belongs to R, then B comma A should belong to R. That is symmetric. Then transitive relation is if A comma B belongs to R and B comma C belongs to R, then A comma C should belong to R. This is the condition for transitivity. Right? I'm just writing this so that we can refer quickly. So I will write various examples where we will write, I'll write different relations and we are going to identify whether it is symmetric or reflexive or symmetric or transitive, or all the three are only symmetric or only transitive, or symmetric and transitive. So all the combinations we will see through some examples. So first example. So examples we are going to see. The first one. Suppose if I am defining a set A is, I am commonly having set A is this. So A set is, suppose 1, 2, 3. It has the elements 1, 2, 1, 3. So that is our A set. Fine. And our A is 1, 2, 3. Suppose I am going to define a relation R as, suppose if I take the relation as R1. Right? Suppose I'm not writing the elements, I'm going to define the relation. I'm going to define the relation here. Right? So I'm going to write it in the set builder form, which means set of all A comma B such that A minus B is less than 2. Less than 2, where A comma B both belong to the set A. Where A minus B is, this is a condition, A minus B should be less than 2, where A and B are from set A. Now, when R1 is given, let's write, now the question is it reflexive? Is it symmetric? Is this relation transitive? We have to check them, whether it is reflexive, symmetric, transitive. So, now R1 it is given in the set builder form. We'll write that in the roster form. Fine. So we'll write that in the roster form. So if we try to write this in the roster form, what do we get? So we get it as A minus 2 should be less than 2. Now what is our Cartesian product? Let's write the Cartesian product. A cross A. A cross A is what? If I write the Cartesian product, 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, then 3 comma 1, 3 comma 2, 3 comma 3. So these 9 elements will be in the set A cross A. Right? So this is your set A cross A. Right? This is your set A cross A, which will have 9 elements. Now we have to check all these elements which satisfy this condition and write it here. Now A minus B should be less than 2. Now let's take this 1 minus 1. So here A is 1, B is 1. Now whichever element in A cross A is satisfying this condition, that will come in this relation set R1. Now let's take 1 comma 1. 1 comma 1 is what? So 1 comma 1 is 1 minus 1. 1 minus 1 is less than 2. 1 minus 1 is 0. 0 is less than 2. Yes. So 1 comma 1 will come. Then let's take 1 comma 2. What is 1 minus 2? 1 minus 2 is minus 1. Minus 1 is less than 2. Yes. So 1 comma 2 will come in the set. Then 1 comma 3. 1 comma 3 is 1 minus 3. 1 minus 3 is less than 2. 1 minus 3 is minus 2. Minus 2 is less than 2. Yes. So 1 comma 3 will come. Fine. Next is 2 comma 1. 2 minus 1 is 1. 1 is less than 2. Yes. So 2 comma 1 will come. So this will come. Then 2 comma 2. A is 2. B is 2. So 2 minus 2 is 0. 0 is less than 2. Yes. So 2 comma 2 will come. So similarly 2 comma 3 will come. Because 2 minus 3 is minus 1. Minus 1 is less than 2. Then 3 comma 1 will come. 3 comma 1 means 3 minus 1. 3 comma 1 means 3 minus 1. This is comma. 3 minus 1 is 2. 2 less than 2. No. So this won't come. 3 comma 1 won't come. Then 3 comma 2 will come. 3 minus 2 is 1. 1 is less than 2. So 3 comma 2 will come. Then 3 comma 3 also will come. Fine. So now we have written the set which is given in the set builder form to roster form. Fine. Now let's check whether it is reflexive. Now for reflexive, what we should take? Every element in A. If 1 is there, then 1 comma 1 should be there. 1 comma 1 is there, yes. Then 2 means 2 comma 2 should be there. It is there, yes. Then 3 means 3 comma 3 should be there. It is there, yes. So therefore we can say R1 is reflexive. R1 is a reflexive relation. You can say relation. Reflexive means a reflexive relation. Because for every element in A, that is 1 means 1 comma 1 should be there. 2 means 2 comma 2 is there. 3 means 3 comma 3 is there. Therefore it is reflexive. Now let's check whether R1, the same relation, is symmetric also. Is this symmetric? Let's check that. Is it symmetric? Now 1 comma 1. 1 comma 1. So I'll erase these. So these are done for reflexive. Right? Now for symmetric, if 1 comma 1 is there, then the reverse should be there. Symmetric is 1 comma 1. What is the reverse of 1 comma 1? Because when A comma B belongs to R, the reverse should also be in the relation set. A comma B, if it is there, then B comma A also should be in R. Right? So here 1 comma 1 is there. The reverse is what? This is A comma B. Reverse is B comma A, which means 1 comma 1, which is there. Then 1 comma 2. The reverse is what? 2 comma 1. When 1 comma 2 is there, its reverse also should be in this set. What is the reverse of 1 comma 2? 2 comma 1. It is there. So this is also okay. Then again take this. 1 comma 3. What is the reverse of 1 comma 3? 3 comma 1. Is 3 comma 1 there? No. 3 comma 1 is not there. Therefore, it is not symmetric. So we will say 1 comma 3 belongs to R2, R1, but 3 comma 1. 3 comma 1 does not belong to R1. Therefore, R1 is not symmetric. Clear? R1 is not symmetric, which means not a symmetric relation. R1 is not a, so this is a reflexive relation because 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there. Right? But it is not symmetric relation. Now let's check whether R1 is transitive. Right? So we have proved that it is, we have seen that it is reflexive, and we have also shown that for one element 1 comma 3 its reverse. A comma B is there. A is 1, B is 3. A comma B is there, but B comma 3 is not there. B comma 3 is 3 comma 1. Sorry, B comma A. A comma B is there, which is 1 comma 3, but it's reverse. So this is A, this is B. The reverse of A comma B is B comma A. B comma A means 3 comma 1. 3 comma 1 is not there in this set R1. Therefore, even if it fails for one of the elements, this condition, we will say it is not symmetric. We may say that it is true for this. If you take this 1 comma 2, 2 comma 1 is there. It is true for this element, but for this element it is failing. 1 comma 3 is there, 3 comma 1 is not there. So if you take 2 comma 3, reverse is 3 comma 2. It is okay for these two elements. 2 comma 2, reverse is 2 comma 2. So this is also okay. So this is also okay. This is also okay. All these are okay. 3 comma 3 reverse, but for this alone it is failing. Even for one element, if it fails, the moment it fails, you can stop. You need not check the other elements. The moment if it fails, but if it passes, then you need to keep checking for the other elements, whether it is passing or not, whether the condition is satisfied or not. The moment the condition is not satisfied, you have to stop and say that it is not symmetric. So here it is failing. This is failing. All others are tick. Only this is failing. Therefore, it is not symmetric. Fine. Now let's check for transitivity. Transitivity, how do we check? We'll take A comma B and B comma C. If such two elements exist in R, then A comma C should also be in R. So what it says is, if A is related to B and B is related to C, the other way to read this is, whenever A is related to B and B is related to C, then A should be related to C, which means A comma C should be in R. Now let's see whether such thing exists. Now let's take example. Let's take, see, we know that 3 comma 1 is not there. Let's take the example of this one. 3 comma 2. See, let's take this. See, if we try to take these two, see, 1 comma 1 is there, A comma B, this is B comma C. So A comma B is there, then B comma C is there, therefore A comma C, which is 1 comma 2, which is there. Right? Or if we take, suppose, let's take these two. 1 comma 2 is there, this is 2 comma 3. So 1 comma 2, A comma B, So it is ending with B, so it should start from 2. Let's take this one. Or even you take this one, 1 comma 2, then it is 2 comma 1, then 1 comma 1 it is there. This is A comma B, this is B comma C. So A comma B is there in R1, B comma C is there in R1, and A comma C means 1 comma 1. It is also there in R1. So therefore it is satisfying for these two pairs. Like that we'll have to keep checking for other two pairs. Every pair. Now let's take these two. Let's take 3 comma 2 and 2 comma 1. Right? 3 comma 2 and 2 comma 1. So let's take this. So we'll say 3 comma 2 belongs to R1 and 2 comma 1, which is this and this. I'm taking. So 3 comma 2 is in R1, and then I should choose an element which is starting with 2. I'm choosing this one. 2 comma 1 also in R1. Then A comma B. So this is your A comma B. A comma B belongs to R1. Then this is B comma C. Right? So A comma B is in R1. Then B comma C is also in R1. So this condition is satisfied. Whenever this is true, then we should show that this is also true. So we have got a pair. Now 3 comma 2 is there, 2 comma 1 is there. Then is 3 comma 1 is there in R1? Is A comma C? A comma C is what? 3 comma 1. Is 3 comma 1 there? The 3 comma 1 is not there. So we will say A comma B belongs to R1, B comma C belongs to R1, but A comma C, A is what? 3, C is 1. 3 comma 1 does not belong to R1. So therefore R1 is not transitive. Transitive relation. It can also be symmetric relation. Fine. So therefore R1 is not transitive relation. Not. Because for this pair is for A comma B is there, B comma C is there. Both are in R1, but A comma C is not in R1, which is 3 comma 1 is not in R1. Therefore it is not transitive. Clear? Now let's take one more relation. Suppose let's take say R2. Another relation. I'm going to define another relation. This is first one, the second one. Right? So second one is, let's take a relation again on the same set A. Suppose I'm going to define R2 as set of all A comma B such that A comma B such that A plus B equal to 4. A plus B equal to 4, where A comma B belongs to A. Now what will be the corresponding R2 set for this? Now it is given in the set builder form. So R2, I will list the elements. Now, which means two elements are related. A is related to B, or A comma B says that A plus B should be equal to 4. Now in these A cross A, whichever gives you 4. So 1 plus 1 is 4. No, this won't come. This won't come. 1 comma 3 will come. 1 comma 3 will come. Then 2 comma 1 won't come because 2 plus 1 is not 4. 2 comma 2 will come because 2 plus 2 is 4. It is satisfying this condition. Then 2 comma 3 will not come. 3 comma 1 will come. 3 comma 1 will come. Then 3 comma 2 won't come. 3 comma 3 won't come. That's it. So this is your R2 set. For this relation, this is the corresponding set. Now is it? The question is this reflexive? Is this reflexive? So reflexive means I should take the element 1 and 1 comma 1 should be there. Is 1 comma 1 is here? No. For every element of A, that 1 comma 1, 2 comma 2, 3 comma 3, all the 3 should be there. Even if one of them is not there, we can stop. Here even all the 3 are not there. So 1 is in A, but 1 comma 1 is not in R2. So we'll say 1 belongs to A, but 1 comma 1 does not belong to R2. R2 is this relation, the name of this relation. Therefore, R2 is not reflexive. R2 is not reflexive. Even for one of them it fails, it is not reflexive. Now let's check whether it is symmetric. Now is it symmetric? Symmetric means what? 1 comma 3 is there, then its reverse should be there. 1 comma 3, symmetric. 1 comma 3 is there, so then its reverse. Reverse of 1 comma 3 is what? 3 comma 1. Is 3 comma 1 there? Yes. Clear? So 1 comma 3 is there. So its reverse 3 comma 1 is there. Right? Then take this 2 comma 2. Its reverse is what? 2 comma 2, which is there. Then 3 comma 1. What is the reverse of 3 comma 1? 1 comma 3. That is also there. So for every a comma b, its reverse is there. 1 comma 3 reverse is 3 comma 1. 2 comma 2 reverse is 2 comma 2, which is there. 3 comma 1 reverse is 1 comma 3, which is there. So for every element, it is true. Right? The reverse is there. Therefore, so we'll say, we can write the definition says, we can say a comma b, in general we can say a comma b belongs to R2 if a comma b, we can write the definition of that to say that it is symmetric. A comma b belongs to R, then b comma a belongs to R2 for every, you can say for every a comma b belonging to R2. So for every element a comma b, its reverse is there. So therefore, so we can say therefore R2 is symmetric relation. Symmetric means symmetric relation. Now next one is a transitive. Is this relation transitive? So how do we check whether it is transitive or not? Let's take an example. Suppose let's take here. Let's take the two elements. So let's take these two. So 1 comma 3 belongs to R2, and 3 comma 1 belongs to R2. So this is of the form a comma b and b comma c, right? And so a comma b is in R2 and b comma c. So wherever it is ending with 3, then should start with 3. So a comma b is in R2, then b comma c is in R2. Therefore a comma c is what? 1 comma 1. But 1 comma 1, is it there here? 1 comma 1 is not there. 1 comma 1 does not belong to R2. Therefore R2 is not transitive. R2 is not transitive. So this is an example where it is only symmetric but not reflexive, not transitive. Why it is not transitive? A comma b is there, 1 comma 3 is there, then 3 comma 1 is there, which is b comma c. A comma b, b comma c, but a comma c, that is 1 comma 1. It is not there in the set. Therefore it is not transitive. Clear? Fine. So this is how we say that it is not transitive relation. Fine. So take it. I will erase this. We will do some more examples. Copy this. Pause the video and copy this. Let me erase this. So we'll take one more example, third example. Let's do the third example. The third example is, suppose A is same set 1, 2, 3, and we are going to define a relation R as A is less than B. R3, third relation I am defining as set of all A comma B such that A is less than B, and obviously A comma B both belong to A. A and B belong to A. Now what is our R3? So the definition is given in the set builder form. So we are writing in the roster form. We are writing in the roster form. So what is the roster form here? The roster form here is that means all from these elements we should take the elements which satisfy this condition. A should be less than B. A should be less than B. So what and all is there? A is less than B. We'll take this. Oh, so it is 1 comma 1 will come. So A is 1, B is 1. 1 comma 1. Is 1 less than 1? No. So this won't come. Then 1 comma 2. 1 less than 2? Yes. So 1 comma 2 will come. Then 1 comma 3. Is 1 less than 3? Because 1 is A, 3 is B. So A is less than 3. A is 1. B is 3 in this. So is 1 less than 3? Yes. So 1 comma 3 will come. 2 comma will come. 2 comma 1 will come. 2 is less than 1? No. So 2 comma 1 will not come. It's 2 comma 1 will not come. 2 comma 2. 2 is less than 2. No. 2 comma 2 1. 2 comma 3 will come. because 2 is less than 3. 3 comma 1 won't come because 3 is not less than 1. So 3 is not less. So 3 comma 1 won't come, 3 comma 2 won't come, 3 comma 3 also won't come. So none of them will come. None of them will come. Only these elements will come. Now we'll check whether this particular relation is reflexive, symmetric and transitive. We'll check that. So how do we check that? Again we will take. So now 1. For this, for A to be reflexive, 1 comma 1 should be in R for every A in A. For every element we take from A, that element should be related to itself. If I take 1, then 1 should be related to itself, which means 1 comma 1 should be in R. Is 1 comma 1 is in R? No. So immediately we can say it is not reflexive. So we'll say 1 belongs to A, but 1 comma 1 does not belong to R3. The relation name I am calling it as R3. So therefore, R3 is not reflexive. Reflexive relation. Clear? Therefore, R3 is not reflexive relation. Not a reflexive relation. Not a reflexive relation. Now let's check whether it is symmetric. Now symmetric, what 1 comma 2 is there means its reverse should be there. That's symmetric relations condition. Right? So 1 comma 2 is there. The reverse is what? The reverse of 1 comma 2 is 2 comma 1. But 2 comma 1 is not there. So therefore it is not symmetric. So we'll say for the symmetric condition we'll say 1 comma 2 belongs to R2, but A comma B belongs to R2, but B comma A is what? 2 comma 1. It is not there in this R3. Sorry, R3. 1 comma 2 is in R3. Its reverse, which is 2 comma 1. Is it in R3? No, it is not there in R3. But 2 comma 1 does not belong to R3. So A comma B is there, but B comma A is not there. But B comma A should be there. Then only it is called as symmetric. If B comma A is not there, then it is not symmetric. So therefore, R3 is not symmetric. Symmetric means symmetric relation. Now let's check transitivity. Is it transitivity? Now let's take this. Now I take 1 comma 2. Now take another element which is starting with 2. This is 1 comma 2. Take another element starting with 2. This is starting with 2. Now 1 comma 2 is there, then 2 comma 3 is there, then 1 comma 3 should be there. Is it there? Yes, it is there. Right? 1 comma 2. And next element you keep your finger here. Then this is 1 comma 2. Then take all the elements which are starting with 2. So this is 2, starting with 2. Right? Put this like this. 1 comma 2. 1 comma 2. Then 2 comma 3. So A comma B, B comma C, then A comma C should be there, which 1 comma 3 should be there, which is there. So if I take these two elements, it is in this form. A comma B belonging to R, B comma C belonging to R. Then I have to check whether A comma C belongs to R. So this is your A, this is your B. This is your A, this is your B. Fine. Now A comma B belongs to R3 and this is A comma B is B comma C. A comma B, B comma C. So A is 1, B is 2, then here B is 2, C is 3. So A is 1, C is 3. So 1 comma 3 should be there. It is there. Right? Again we should check for every pair. Now let's take 1 comma 3. Now second element. Is there any element starting with 3? No. So we are not able to find such two pairs. If we are not able to find such two pairs, it is okay. We will move on to the next one. 2 comma 3. Anything is starting with 3? This is ending with 3. If I take this element, for this I need to find, if I take this as A comma B, then I should find B comma C. B comma C means 3 comma something. That is not there. So it's okay. So whenever such pair exists, then A comma C should be there. Right? Therefore it is transitive. So we can, to prove that it's transitive, we'll write the definition of transitive because we have checked it. If such a pair exists, then A comma C belongs to R. Whenever A comma B belongs to R and B comma C belongs to R, then we see that A comma C is also in R. Right? In case if you are not able to find such two elements, it is okay. Then we cannot say it is failing. No. Whenever you are able to find such two elements, the third element should be there. If you are not able to find the two elements, then it is okay. Still it will be transitive. Which means we will not consider those two pairs, which are not. Suppose I can take this as A comma B and this as B comma C. Because this A comma B means it should start from 3. So which means we can't take these two pairs. So you don't need to even check anything here. Try to choose that all the pairs which are like this. Then A comma C should be there. So here we will write the definition. So here we will say A comma B belongs to R and R3. Generally we will write, and B comma C belong to R3 if A comma belongs to R3 and B comma belongs to R3, then A comma C belongs to R3. Therefore R3 is transitive. Therefore R3 is transitive relation. Fine. So here, or we can take these two pairs and say this comma this belongs to RC. Generally, whenever you are proving that it is transitive, we don't give some example and say it is satisfying for this. It should satisfy for every such pair. So here we have only one such pair, and that pair it is existing, which means it is true for every pair, because we have only one such pair. If it is true for only one such pair, there is the only pair that is available, which is these two, 1 comma 2 and 2 comma 3. That gives you A comma C. Then it is true for every pair, because that is the only pair that we have here. Right? So therefore, we can say R3 is transitive. The relation R3 is a transitive relation. So here it is not reflexive, not symmetric, but it is transitive because this condition is true. Any two elements in this form, if I take, then A comma C is also in that. Fine. So I will stop here. You can watch the next video for the continuation of this, where I will do some more examples with reflexive symmetric, so that you become very clear on these three types of relations. So see you. Please watch my next video for the continuation of this. Thank you for watching.